Welcome back to Weather Analysis with Mr. CB. If you've been following along with this series, sorry that it's been kind of a long time since I made the last one, but there's been a lot of things coming up, and I only was able to get to the continuing this series now. But let's continue on. So we're going to talk about once again another level of the atmosphere. If you remember what we talked about before, it was the 300 millibar level. So if you need some review on that, maybe go back to that video and learn or relearn what can happen at the 300 millibar level. So just in case you don't remember pressure decreases as you go up. So each level that we're going to learn about from here on out is going to go down until we get to the surface. And this is the next one that we're talking about. So it's a little bit lower than the other one, 500 millibar level. Now, the level that this is at is approximately 18,000 feet or 6,000 meters. So I say approximately because if you remember on the maps, anytime we have a pressure map, there's going to be lines on that map that are ISO heights. So remember the map everywhere on that map is going to be 500 millibar, but there's going to be different lines that will have values that are going to look like they say something like 500 something or 600 something, but really what it is, you add a zero to that. So it's really going to be something in the upper 500s or the lower, or sorry, upper 5,000s or lower 6,000 in meters. So the map's going to show meters. What can we see at this level? Well, actually, the most important thing is this down here, vorticity advection. Vorticity advection. We already talked a little bit about vorticity before, but specifically, there's two types of vorticity advection that you can see here, positive and negative. And in a future video, we're going to talk about basically the purpose of learning all these things, like positive vorticity advection is here, negative is here, is combining what we know on each layer is going to help us be able to have a potential forecast. That's the purpose of looking at these different things because one thing at one layer is going to mean a different thing for a different one, and you just combine them together basically. But we're going to see still some troughs and ridges here. Um, we can see different orientations of the troughs and ridges, which I admit that I didn't talk about as much as I wish I did. So let's actually look at that real quick. So if we have a trough like this, you can have a trough axis. And the trough axis you might describe as a dotted line like this, or you might identify as that. And one that's like that is just going to be considered neutral. But you might have a different situation when the trough's more like that. And in this case, we would call that positively tilted. And the reason why is if you consider that axis a line, like, you know, it has a positive slope. Another way around if it was negative. So the same thing can be the case for ridges, but ridges we would usually use a zigzag like that to identify the axis for the ridge. Um, Another thing that we can identify here is short waves, though we can also see that at a different level we'll later talk about, but we can also see short waves. So let's, oh, so we also have upper air plots here, just like we do. So you probably know about the surface ones. That might be the first that you learned about. Then we also learned about the 300 millibar upper air plots. And what do you know? These look the same, right? And it's true that yes, the same four things are displayed in the same four corners. Um, Here is just going to be the temperature in Celsius that there is at that area. The DDDD, that's just not very fun to say. But that's going to be the dew point depression, not the dew point. That's what it is at the surface. But for these upper millibar, these pressure upper air plots, it's going to always be the dew point depression in that lower left. And if you don't remember what that is, that's actually just going to be the temperature, or sorry, the difference between the temperature and the dew point. So let's say this TT up here was, it said, I don't know, 2, just a random example. If it's 2, that means temperature is 2 degrees Celsius. If this thing said -1, then it means the difference between the temperature and uh, dew point is -1, so that means that the dew point is 1, because you do -1, if that's what that said. Then the HHH, the reason why that we describe that as 3 H's is because it's always a 3-digit number. They just don't want to limit the text that they have to put to where it would just have too much text and block. They end up just putting 3 numbers instead of 4. So if it said 589, then it's going to be 5890 meters. And then those two P's, that's not something that we really talk about that much right now, so you don't have to worry about that, but it is the 12-hour height change. Uh, so at this 500 millibar level, for our troughs and ridges, there's two different things that can happen and at these mid levels. And for the troughs, we can have them deepen or fill. And you know that a trough is filling if you have the faster winds before the trough axis. So you see that it's before it or not yet on the other side. That would mean that it's deepening still. Um, that means there's going to be a deeper valley, so it's going to end up more like that. Um, and there's going to be cold air advection taking place in this situation. Really, more that we can know about this would be at a lower level, which is the 850 level. We'll talk more about that later. The 850 millibar level, we can know more about thermal advection there. So really, this thermal advection is I don't really need to explain that right now. We'll talk about that in the next video. So, but regardless, it's you just want to know that cold air advection is going to be present when we have a deepening trough. And you know it's deepening trough is if these faster winds are not yet passed. Um, and that's what I just said, the jet max. There's going to be a stronger gradient. And sometimes this can be the beginning of an MLC. What is that? Mid-latitude cyclone. Now, as you might expect, luckily some of these things in this course so far you might notice are just flip of the other. So if you remember one, you remember the other. Um, And filling, a trough is filling, which really means it's getting less of a trough, and that's if they're like bye-bye, they're going away, they're on the other side of it, the jet max. And you're gonna have warm air advection in this case. Ooh, I hate it when I do that. I'm sorry. Sometimes I just copy and paste text and I forget to change it. So the trough, this makes the trough deeper, this makes the trough less deep. So sorry about that. I always have I always tend to do that. I like copied and pasted it and forgot to change that part. Um, Weaker gradient, and this can be the end of a mid-latitude cyclone. So that's the two types of troughs that you would want to know. Now, ridges, sorry, I was supposed to push the L for laser and I accidentally did, what is that, semicolon? Didn't know if that was going to do something bad. Um, Mid-level ridge. So you could have two types of mid-level ridges, intensifying or weakening. It's going to be intensifying if the fastest winds are not yet at the ridge. They're before it. And for one thing, you might think, if you don't remember, how would you know that it's not yet there? You can see the way the arrow's pointing, but it's also because generally, due to some of the forces that we've already talked about, the flow of the winds is going to be from west to east anyways. So that's how you might know that uh, that's how you would know that that it's not yet at the ridge peak. Um, and you're gonna have warm air advection in that case. Cold air advection um is gonna be when it's weakening, and that's if it's on the other side of it. And I say air from north, air from south. That is coming from the south, and it's coming from the north in that case. So that's why it says that. Um, now let's talk about what a parcel is going to do at its highest vorticity. there's going to be usually precipitation ahead of highest vorticity. So it's important to note that when I say ahead of something, um, something that's basically if it's east of the highest vorticity, then that's what we consider ahead in this case. Um, so what a parcel is going to do is, because it's increasing speed, a good way to imagine this is a ice skater. So an ice skater, if they want to spin faster, they usually will go like this, kind of converge and make themselves less wide, right? And that's what happens to the parcel. It's going to be elongated like that, and it's obviously higher vorticity right here at this base of the trough. So the precipitation is going to be identified as around here, and it will go back to normal as it gets on the other side. But that's why it elongates, um, because it has higher vorticity, and then the reason why it gets narrower is just like the analogy I said about the ice skater. No, sorry. And where in this trough is the negative vorticity advection and the positive? Um, you could also identify that as cyclonic or anticyclonic. So AVA, CVA, you can also, it's synonymous. So, um, positive vorticity infections is always going to be on this right side of the trough, negative on the left side. And negative, it means there's going to be low vorticity moving to where the high vorticity once was. So the high vorticity was here as it was moving along. Now the negative creeps in. The positive vorticity advection is the opposite, where the high vorticity advection moves, or high vorticity moves where the low vorticity once was. And the action of moving is what we identify as advection. That's what advection is in this case. The next thing we'll talk about is short waves, and actually the last thing. We can see these here, but uh, best at the 700 millibar level. So we're going to talk more about this actually later. But you can see short waves here. And when you see short waves, they're going to look like something that seems out of the ordinary. Um, Basically, it's seen as an interruption in the flow. So you see this right here, this ISO height's like, okay, that's normal, normal. But what about this one? This one's just like suddenly like, doo, it just goes way down like that. That would be a short wave right there. And where these are will have additional lift. So it's a localized area of lift, and it's going to be related to thermal advection, which we'll talk more about in a future video because you can see that better at a lower level. But for now, what you just want to know is that at this level, we can see a short wave, and it's if it looks like that, where there's an interruption in the flow. All right, that's going to be it for this video. Thanks for watching.